Well, thank you so much for the invitation to come here today and share some of my science with you. I'm really excited in particular to talk to this community about this work because I know you all are the folks on the ground looking at this every day. And the first time I saw the aurora was actually during the May 10th storm, which was the weekend of my graduation. So I took it as a little present to me, congratulations on graduating. Now you've seen the aurora, now you're a real agronomist. Um, and I hope to see it obviously again. But in the meantime, let me tell you about the study that my colleagues and I did the past year or so, looking specifically at the optical spectrum of Steve and the picket fence and trying to figure out what we could about the mechanisms creating the picket fence in particular from the spectrum. If you've seen other things, I've been calling the picket fence an imposter aurora. And just to give some background there, I'm going to just go over just a common definition so we're all on the same page about what I mean by aurora and then what I mean by an imposter aurora. So might as well look at some pretty pictures while we do that. So when I'm talking about the aurora itself, we're considering that to be the lights that are produced by particles that are energized hundreds or thousands of kilometers above out in space, in the magnetosphere. So above where you're seeing the actual light. So these electrons or sometimes protons are getting energized out in the magnetosphere by a variety of processes. They're streaming down along Earth's magnetic field, colliding with the upper atmosphere, essentially heating up the upper atmosphere. So knocking some of those atoms and molecules into excited states. And then when they relax, they're releasing that light that we see as the aurora. And so the key thing here is that regular quote unquote aurora is created when particles are energized hundreds or thousands of kilometers away and then come in and hit our upper atmosphere. So as you all know, Steve and the picket fence are relatively new to the science community. They only were brought onto the scene kind of in 2018 with Liz's paper was the first big one, at least in the scientific literature. And when they first came about, it started this debate, right, on how the emissions in Steve and the picket fence are generated. Steve, it was pretty clear pretty quickly that it was different from an aurora, right? These are all in the subauroral region. And also the colors, the emission spectra are different from what we expect. In addition to that, they are co-located with these very fast flows of ions in the subauroral ionosphere. And so it's likely that the emissions are related to that. And I'll talk a little bit more about that. The picket fence, though, if you search the early literature on this, folks looked at the picket fence. They saw that it's green. Most normal, quote unquote, regular aurora is green. And so a lot of the early literature assumed that the picket fence was generated by particle precipitation, similar to the regular aurora. And so initially it was thought that, Steve is something else, Steve is something new, but maybe the picket fence is something that we're familiar with. That was something that we interrogated with the recent paper. And the evidence that we were looking at is specifically the optical spectrum. And if you look at the optical spectrum, there are some differences between regular green aurora and the picket fence. And so to point out those differences, the first thing I want to do is just take a look at a spectrum of a regular aurora and then look at some of the normal features and then contrast that with the spectra of Steve and the picket fence. So a typical quote unquote green auroral spectrum looks something like this. So on the x-axis here, we have the wavelength of the light, or there's a convenient rainbow for those of you who don't read wavelengths. These are all in the optical spectrum. And then the y-axis here is just the brightness, so how much of that light we have. Unsurprisingly, the dominant feature that you see here, the brightest thing, is this green line, which is created by atomic oxygen. This is when electrons are striking atomic oxygen, or there's a couple other ways to excite it. But this is the dominant feature. This is why your typical green aurora looks green. You also have some other features in here. You have this red line from atomic oxygen. This is actually more dominant at higher altitudes. So the higher altitude aurora often looks red because this feature is dominating here. You also have this banded structure. This is from the nitrogen first positive group. So just so this is when there's two atoms of nitrogen, diatomic. Nitrogen is creating this when it is excited. And then over on this end of the spectrum, you have these blue emissions, and these are actually created by the ionization of nitrogen. So when a particle hits nitrogen hard enough to knock off one of its electrons and also excite the ion, that's when these blue lines are created. So this is your typical auroral spectrum that you have. When you're looking at the spectrum of Steve, of course, it looks very different. So here's what that looks like. Oh,
Could
yeah.
I ask you,
Go
so the
ahead.
blue lines and the red lines, those are from a little bit of nitrogen, kind of largely lower in altitude than the oxygen, right?
So this is all roughly from the same altitude. But there's nitrogen up there. There's also atomic oxygen up there. I think I don't fully understand your question, maybe.
Is there an altitude range for this specific measurement, or?
This specific measurement is from a spectrograph just integrating along a line of sight kind of close to the horizon. So it's cutting through several different altitudes here.
Okay. Yeah, I was just kind of trying to, maybe you could say a little bit more about the nitrogen and the oxygen just kind of overlapping in space a little bit.
Sure.
Or yeah.
Yeah, I mean, so obviously down here, you don't have a lot of atomic oxygen, but you do have a lot of nitrogen, right? The air we breathe is something like 70% nitrogen. As you go higher, right, the higher you get, the neutral atmosphere starts to separate by mass, essentially. So those heavier elements like nitrogen or like, you know, the type of oxygen we breathe, which is O2, as opposed to atomic oxygen, which is O. Those will decay. There's less of them the further you go up, and suddenly oxygen is much more dominant, just atomic oxygen. But you still have nitrogen and oxygen at the same time. It's just that once you get to auroral altitudes, you have more atomic oxygen than nitrogen. There's an altitude at which they sort of cross their equal densities, and then there's more oxygen. But you have both of them up there, kind of at all auroral altitudes.
And these two are two different chemical transitions, or like the chemistry gets really complicated with the colors. That's why I'm just kind of wanting to.
Yes, and I'll go into it a little bit more when we look at the spectrum of the picket fence to try to draw some of the distinctions here.
Okay.
But essentially, it takes a different amount of energy when you're striking either atomic oxygen or nitrogen to create each of these features. And we can actually extract some information from that, and I'll talk about that more.
Was there somebody else that had a question?
I think I heard another question.
No, not a question, but related to Liz's question. I think what you're seeing here is some kind of altitude profile. Being a line of sight, growing close to the horizon, you will be sampling from lower altitude, and different small regions, you will be getting light that will give you N2 plus, light that will give you N2, first positive, green line, and maybe higher, the red line, the oxygen.
Yes, yeah. So this oxygen red line, right? It tends to be at higher altitudes. I think because we are looking at a line of sight with this measurement, it's probably from the higher altitude, because at lower altitudes, essentially it doesn't survive long enough in that excited state to actually emit the photon. Yes, so I think that's what's happening here. And when you see the picket fence, we don't see any of that oxygen red line because the picket fence happens at lower altitudes. But just for this example spectrum, none of that background has been subtracted, essentially.
Yeah.
So good question.
if I could say one more thing. So
sure.
I think we typically call the green line or the red line like characteristic 55, 77 angstroms here for the green line. It's like a typical, like it's easy to refer to that as the green line and think that the normal aurora is just that green. But as the spectrum shows, it's a blend of a little bit of other wavelengths as well. So
yes,
yeah,
absolutely.
just wanted to add that. Thanks.
Yeah, so the green is the 5577, this red is 630. Nitrogen first positive is kind of banding above that and actually extends farther into the infrared as well. And then you have the blue lines down here. But yes, even though normal aurora looks green, it is a mix of lots of wavelengths like Liz was saying. Okay, so this is the typical green auroral spectrum. I do want to show you a spectrum of Steve just because it's interesting. This is what the Steve spectrum looks like. And the features you'll note here, right? You have a little bit of this oxygen red line. Steve is at a high enough altitude that this is probably real, this persists. It may or may not have green line. You'll see that this is kind of within the uncertainty of our background subtraction. So it's a little hard to say. But obviously the interesting and dominant feature for Steve, right, is that you have this continuum of emission, which is to say that at all wavelengths, you have light that is above the background level. And that's why Steve appears whitish or purplish at times. There are a couple theories out there as to how this continuum is created. I think the leading theory is one that was published by my colleague Brian Harding a few years ago. Although even that theory, there are some problems that do not match up to recent observations. So we're actually going back and redoing some of that work and trying to figure out what's going on with that. I'll allude to essentially one of the problems is this recent paper that came out by Toshi Nishimura shows a lot of very fine structure in Steve. This is high resolution video of Steve, and you can see it's not just a smooth arc, right? There's a lot of substructure in here. And the emission time scale, so how long it takes to produce the light, based on the previous theories we had for that continuum emission, suggests that Steve should be a nice smooth arc, just because it takes a while to emit the light. And it wouldn't necessarily predict this substructure that we see, which is to say that the real excitation mechanism really remains an open question. There's not a definitive theory out there yet. That's still something we're working on. But so my work was mostly on the picket fence. I'm going to go back to that. So just to remind you, here's the typical green auroral spectrum. And then if we're looking at the picket fence spectrum, it's going to be different. But first, let me just do a little bit more information on this. So as I mentioned, to get each of these features, it takes a different amount of energy. To get this primary green line, essentially you need about 4 electron volts of energy. So a particle with about 4 electron volts to strike an oxygen atom and knock it up into the excited state where it will make this green line. For the red line, it's about 2, but again, we're not going to see that just because of the altitude in the picket fence, so don't worry about that one as much. For the nitrogen first positive, it takes about 7 electron volts. And then over here to ionize nitrogen and create this blue line emission takes about 18 electron volts, right? So the ones to remember, green is 4, nitrogen first positive is about 7, blue is about 18. And when we have this typical aurora, right, just for particles to be accelerated along the field line and make it deep enough down into the atmosphere to create these emissions that you're seeing in the typical aurora, so at about 100 kilometers above the surface of the Earth, they need hundreds or thousands of EV to get down there, which is to say that in a typical aurora, you are pretty much always going to see all 3 of these emission features. There's enough energy in the particles that are getting down that low that you're going to get the green line, you're going to get N2 first positive, and you're also going to get some of this blue line emission. So now let's take a look at the picket fence spectrum. So here's what this looks like. There's a couple of features. First of all, you'll see that the dominant feature, as you would expect, is this 557.7 nanometer green line emission. You actually do have a hint of this N2 first positive over here. It doesn't look as clean as in the aurora, mostly because there's not as much of it. But you do have a hint of that there. The smoking gun, though, is that you don't have any of this N2 plus first negative emission. We've looked at multiple examples of this. This is the median for a lot of examples on a single night, and we don't see any of those blue line emissions. And as a result, that means that this can't be particle precipitation, because if the particles were precipitating down to these altitudes, again, you would have enough energy to create some of these emissions. Therefore, we say, is this particle precipitation based on the spectrum? Probably not. It's too green, as we say. And just by looking at, the energy that it takes to create each of these features, we can say that, well, in order to get this exact spectrum, we probably need a population of electrons that have energies between 7 and 18 eV. So enough to create this N2 first positive, but not enough that you would start ionizing nitrogen and creating this blue line emission, which we don't observe. And that type of a population is not consistent with precipitation. I guess I'll pause there and see if there's any questions before I go on to some of the observations and modeling work that we did.
Yes, I have a question.
Okay.
Can you describe briefly how do you select the geometry? Because you need your slit going right through the picket fence, right? And the picket fence is very small in size. So how do you select the right condition?
Yeah, so actually, I think the next slide is going to help me answer. Well, okay, we'll skip. This slide is going to help me answer that question. So we're using data from the T-Rex spectrograph up in Lucky Lake in Canada. This is a kilogram, right? So there's time along this axis, elevation angle on this axis. For this study, we were picking out these observations of the picket fence that you're seeing. Each one of these points represents an entire spectrum. And so we're picking out essentially at each time stamp from these individual spectra. And we're looking specifically at ones that are lower down on the horizon. There's also a picket fence up here. This is the one that was in Meg Gilley's 2019 paper. But we're using these so that our line of sight is piercing through almost a single altitude, so that we don't have to worry about sort of the profile of the light. We're just looking more or less at a single altitude here.
Okay, thank you.
Yeah. Okay. Other questions?
I put a question in the chat, perhaps for some of the photographers. I'm curious. I know some people have looked at some of these images of the picket fence and kind of noticed what you're pointing out, that it's more green and maybe a little less blue than the usual aurora. And I guess I'm just curious if that other folks have gone back and noticed that in the color as they photographed it or looked at it afterwards.
Yes, definitely. It's more on the green side.
That's great. Yeah.
It's probably not something you can tell by the naked eye. Maybe you can, because you all see a lot more aurora than most of the space scientists.
Yeah, I
But
just, oh, sorry.
go
Can I
ahead.
jump in just for that question? Yeah, it's with the naked eye, no, not for me, but in the camera, definitely a more vivid green. So, yeah.
All right. Okay, so right, from the spectra, we concluded that it's probably not particle precipitation because it's too green, like I was describing, and like you all were just chiming in there to echo. So the other idea is maybe the electrons get their energy essentially right where you're seeing the light. So it's in situ electron energization. One way to do this is that if you look at a couple of the recent papers, Christina Lynch had a paper, and then there was a Mission and Streltsov paper in 2022. They were looking actually at the structure of the picket fence, and they were suggesting essentially that there are various instabilities in the plasma up there that can cause the structure of the picket fence. And a byproduct of those is that there might be low altitude electric fields right where you're seeing those emissions that are parallel to Earth's magnetic field. So they're along the magnetic field, and that perhaps that could energize the local electrons. But they didn't, go out and show that that source of energy, when applied to the electrons, could produce the specific spectrum that we're seeing in the picket fence. And so that's really what this study is about. The question, can parallel electric fields energize those local electrons that are actually already there and drive picket fence emissions? So that was what we sought to answer that question. As I mentioned, we drew observations from the T-Rex spectrograph. I already showed you sort of the average spectrum from that. These are the ones that we were picking out to do that. And what we were doing is we wanted to find what is the ratio between the amount of green line and the amount of N2 first positive that is created, and use that number, that ratio, to try to constrain a model that we're creating of the emissions that would be generated driven by parallel electric fields. And at the same time, another constraint is that we can't have any of that N2 plus first negative, any of that blue line created. So this is what that ratio looks like, looking at the green line luminosity on the x-axis here, that N2 first positive, so the red luminosity up here. And then each of these points is one of the points, one of the spectra that we were looking at. And so then again, our question is, can that model driven by parallel electric fields recreate this ratio that we're seeing between green and N2 first positive while also not producing those blue line emissions.
Can I jump in?
Yeah,
Sorry.
sure.
So I was just trying to type, sorry, I don't type as fast. But when you say the local electric fields,
Yeah.
the aurora that is driven locally, like kind of what that means is at the same height as where the light is actually being produced. So at the same height as the picket fence, within it, basically. And so like, and then the electric field that you're talking about is the amount of a voltage that the particles would actually be accelerated enough by a few volts to produce the colors, the green line and this other other one in the specific kind of expected sort of amounts, like a little bit of the ratio that would be characteristic. So I just wanted to like add a little bit more, if that helps at all for anybody, of what that means. And then let's see, can you get an intuition of parallel electric field direction compared to magnetic field lines?
Yeah, so parallel, when I'm saying parallel electric fields, I mean it's parallel to the magnetic field, which means that, you know, if the magnetic field up in the auroral region is going essentially straight up, the electric field is also going up and down. And under this theory, wherever you see the light is exactly where the electric field is in space. So the picket fence has that characteristic pattern, right? The on, off, and it's constrained in altitude. And so that would be the same as the electric fields that we're theorizing might exist there. It would look the exact same as the profile of the light you're seeing, essentially.
And effectively map it out, right? That's like what's really cool,
That's the
potentially.
idea, yeah.
Yeah.
Exactly.
And then the question is, where does the electric field come from?
That is something that I will address a little bit at the end, but let's just accept the fact that maybe there's a parallel electric field there, look at the consequences, and then talk about where that might be coming from.
Cool.
Good questions, though. But I don't want to jump the gun too much. All right, are we good to keep going for now?
Sorry
Okay.
to keep interrupting. Sorry.
No, it's okay.
Trying to get my head around it and also like add a little bit more.
No, very happy to clarify all of this stuff. All right, so the next part is looking at the specific modeling that we did to try to replicate essentially this ratio that we're seeing. Happy to talk more about this as well. I don't include too many details here, but essentially what we do is we have a realistic neutral atmosphere. So we have the nitrogen, we have oxygen, and a couple of other species up there. And we have the ionosphere, so just ambient electrons and ions up there, although we're only tracking the electrons. We go ahead and apply a parallel electric field to it and see what that does to the energy distribution of the electrons. That's what this plot is showing here. So this is electron energy. How much energy do they have on the x-axis? On the y-axis, this is kind of just the probability that you'll find an electron with that much energy. And the values here are values of the electric field. So the thing to take away from this really is that as I'm turning up the electric field here from 20 to 60 to 115 to 170 millivolts per meter, this black line, which is representing the distribution in energy of the electrons, is essentially getting stretched to higher and higher energies. You can see that here. So sort of the tail of this distribution that you're seeing here is going to higher and higher energies. And the interesting thing here, I've also plotted essentially the cross sections for exciting these emissions that we're seeing, which is to say that, you know, this green line here, right, is telling you this is the cross section for the oxygen state that would create the green line, basically. And so if the black line here is intersecting this, that means that you have electrons that could collide with oxygen and create the green line, right? So at 20 millivolts per meter, you can't excite any of these, either the green or the N2 first positive, the red, or the blue, the N2 plus first negative. But when you turn it up to 60 millivolts per meter, suddenly you can start to get some green line. You can get maybe a little bit of red. You still don't get any blue. As I'm turning it up now to 115, the ratio between how much green and how much red I get is going to change. And I still don't make any blue. If I turn it all the way up to 170, again, the ratio is changing between red and green, but now I'm actually starting to ionize nitrogen and create a little bit of this blue. So essentially this modeling is helping us get a natural constraint on one, is it possible to make the ratio that we see without making any blue? And two, if so, we can get an idea of how strong that electric field has to be from this modeling. Happy to answer questions about this or go back to it later, but hopefully that was an okay overview of the modeling section of this.
You have a little question in the chat about what is
Okay.
the plus versus positive and the plus versus negative, and just the, the things that are, I don't know if there's other labels on this chart also, but some of the conventions of, yeah, go ahead.
Yeah, so this O1S is essentially just telling you, so the things in parentheses here are kind of the notation that chemists use to denote different excited states of these atoms and molecules. So the nitrogen first positive is essentially created when the N2, this is the B triplet state, essentially, when that gets excited, and then that falls down into the A triplet state. The chemistry here, it gets pretty hairy pretty quickly. But essentially, the important thing here is just that, you need something to smack nitrogen and move it up into this B triplet state, which takes at least this, approximately 7 electron volts, a little bit more to do it. But
Yeah.
anything with higher energies can do that too.
Sorry, I think the question is more basic.
Okay,
In fact, for me, it would help just the distinction between first positive and first negative.
sure.
So one is neutral and one is an ion, right? But
That's correct.
why do you call one positive, the other one negative, or just that basic?
The positive and negative, that is actually a chemistry convention that I'm not entirely sure why it's being used, to be honest. But yes, when you're talking about one being a neutral and one being an ion, yes, the nitrogen first positive is when we're exciting just neutral nitrogen up to that triplet state. The first negative, N2 plus first negative, is when an electron is hitting nitrogen hard enough to both knock off one electron and also leave the ion in an excited state, which then decays and releases that blue light. How was that?
That was good.
Excellent.
Yeah.
Okay, cool, great. All right, so that's what we did for the modeling, and the results of that were this. So here you're looking at the strength of the parallel electric field on the x-axis. You're looking at the altitude on the y-axis, and so this is taking into account how the composition of the atmosphere is changing with altitude. And then the color that you're seeing here is the ratio that we have between that N2 first positive and that green line. This is the part of the parameter space that we modeled. So down here, the electric fields are so small that you don't even get that green, like we were seeing in that other plot. Up here, the electric fields are essentially too large to be realistic, and so we weren't modeling that area either. But so you can see the ratios that we modeled. That observed ratio that we got from those spectra is plotted right on here. It's 0.34 that we saw. And at about 110 kilometers, which is the altitude that other papers have said, the picket fence is probably around this altitude. Essentially, we can recreate that observed ratio if we have electric fields, it says here, between about 80 and 150 millivolts per meter at this altitude. Those electric fields are pretty high, but they're not ridiculously high. And so from this, what we took away was essentially this parallel electric field hypothesis is viable. This might be what is creating the light in the picket fence. And in fact, if we have those fields between this strength that we're predicting, you would get the exact spectrum that we see in the picket fence. Any questions there?
I have forgotten, this is probably a dumb question, the direction of the electric field. Like, it's going down, right? The same as the usual.
This works if it's either down or up. Yeah, just as long as it's along the magnetic field.
Do you have a prediction of that from your theory?
The theory doesn't care whether it's down or up. In fact, it could even be alternating, kind of switching up and down, as long as it's doing so on a time scale that is larger than the time it takes for the electron distribution function essentially to equilibrate. So for the electrons to get into that sort of steady state of different energies, which is very quick. It's like a fraction of a millisecond.
Yeah, I was kind of thinking about whether observations of the picket fence show any altitudinal motion preferentially.
So we're not, at least in our modeling, we're not including transport, which means that we're not tracking whether the electrons are moving really far away from where the electric field is. Although our initial assessment suggests that they're not moving very far. But if we have plans to expand this model a little bit, take that into account, and then maybe there would be something observationally that we could look at, but we're not sure right now.
Does the electric field moving up or down affect whether it starts from the bottom, goes to the top, or top and going to the bottom, or make no difference? Can you hear my question okay?
I can hear you. Yeah, thanks for your question. The direction of the electric field would affect the direction of transport, but again, we're not considering transport as part of this model. And we also think that the transport, it's not very far. So essentially, we're saying that right where you have the electric field, whether it is up or whether it is down, you're going to get the same light, more or less.
All right, thank you very much. Is that true in general about electric fields in the aurora, up and down all the time?
So when you hear parallel electric fields normally associated with aurora, you're talking about the auroral acceleration region, which is out of the magnetosphere, so several thousand kilometers away. And with those, the direction matters more or less because it's the direction that you're going to be accelerating particles down. But these fields are different because they're actually in the ionosphere. They probably have a different source.
Great, thanks. Very clear.
Great.
One more question on this. You mentioned something about the nature of these electric fields that could be oscillatory. And I'm saying picket fence is not like a continuum or uniform emission. So you have a pocket, nothing, pocket, nothing. Is that's a sign of the oscillatory nature of the electric field that is not changing in altitude, but in longitude or latitude, depending how your picket fence is occurring, or that pockets of greens are not related to the structure of the electric field?
So the spatial structure of the electric field would reflect the spatial structure that you're seeing of the picket fence under this theory, which is to say that you would have a parallel electric field and then nothing, and then a parallel electric field and then nothing, kind of in that picket fence structure. But that is not necessarily related to whether the electric field itself is turning up and down, whether it's oscillatory, right? There's a spatial structure and then there's temporal structure.
Yeah, okay, thank you.
Yes, thank you. Okay, so I think I'm using up all of your time here, so I'll go ahead and continue, and then I'm sure there'll be more time for questions. I want to mention that in the course of doing this research, we ran into some things that looked kind of like the picket fence, at least from a spectral perspective, but are in the aurora itself. And so this video was actually taken by Vince, so thank you, Vince. I know you're on the call right now. But so this is what we call the enhanced aurora. And the thing to see here, right, is that we have sort of this, continuous change in the brightness, but then all of a sudden we have this discontinuity in the brightness. And the bottom of this aurora is much brighter than above. And it's really this discontinuity to pay attention to, because models of precipitation, so the particles, coming in from the magnetosphere, could not predict this discontinuity in brightness. It should sort of slowly get brighter and brighter until the bottom, and then it disappears at the altitude at which particles can no longer penetrate further. So in explaining, and also if you look at the spectrum of this HEM, or this enhanced part at the very bottom, you'll see that it is also too green, or at least some studies suggest that it is also too green. Some modeling that was done by Thomas Carlson in 2005 actually looked at the electrodynamics of the aurora and suggested that, parallel electric fields, just like what we were looking at for the picket fence, might be arising in the what's called the downward current region in the aurora, which is kind of like the spot that's a few kilometers away from where the electrons are coming in. It's kind of when they're going back out, more or less. And so he suggested, yes, there might be parallel electric fields there, and they might be creating these emissions. But again, it wasn't until now that we have a model showing that, the spectra, at least for the picket fence, can be explained quantitatively by those parallel electric fields. And on top of that, back in the 80s was the last time there was a statistical study of these. And that study suggested that things like this, these brighter layers, not necessarily the big hem here on the bottom, but just brighter layers embedded in the aurora, might happen as often as 50% of the time that the aurora is visible. And big magnetospheric models of the aurora don't currently include this kind of thing at all. So this might be more important than we think, essentially. And not very much is known about it. And so right now, what we're planning, actually, we recently proposed a rocket campaign to NASA to attempt to shoot a rocket through the enhanced aurora for the first time. So our idea is, essentially these parallel electric fields have never been measured. And we want to see if they're actually there. If this, even though on paper this is viable, the theory is viable, they've never been measured. It's never been verified that they're there. So we proposed a rocket campaign. We still haven't heard about funding, but we should hear in the next couple of months, hopefully, whether we got funded or not. To help us prepare for this campaign, we actually really need to better understand enhanced aurora and when they tend to occur and how long they persist. Essentially, do we have a good shot of hitting one with a rocket? And on that, one of the reasons I was excited to come talk to this community is that we'd love to collaborate with citizen scientists in the Aurorasaurus community to help us answer those questions about enhanced aurora. And so I'd be, very open to chatting more about that, or if anyone wants to email me after. But for now, I'll open the floor to questions, and thank you for your time. This is the summary. If you haven't seen the paper yet, you can get it from the QR code here. And other than that, thank you again for your time, and I'm happy to take any questions.
Thank you, Claire.
Really great. Super clear. Thank you for the wonderful explanation. So just so that I'm clear on the understanding, the enhanced aurora could potentially be caused by the same thing that's creating the little green things, the picket fence with Steve. Is that correct?
That's right. Based on the spectra, and we still need to do a more comprehensive study of that. That's actually something that's ongoing right now. But we think that it could be those parallel electric fields, the same source that's creating the enhanced aurora as well.
That would be wonderful.
I think so too.
I hope you get your rocket.
Thank you.
There was a great question back in the chat a little bit. Rocky, I'm not sure if your mic works. Let me see. Rocky was asking if there was any information on the amount of infrared emitted by Steve, and can the picket fence be related to heat from the infrared or any of those other wavelengths too?
So to my knowledge, there have not been measurements of Steve in the picket fence in the infrared. There are a couple of studies that are looking at Steve in the ultraviolet, so the more energetic, the shorter wavelength side of the spectrum. But the infrared is kind of a bit of an unknown at the moment. Those N2 first positive emissions that I mentioned, they actually extend out into the infrared, so it's likely that you would at least see those there for the picket fence. But other than that, unsure. It's not clear how far for Steve, for example, how far the continuum extends in either direction, either into the infrared or even into the ultraviolet. The observations there are just of specific features, but not necessarily the whole spectrum. So it's kind of an open question.
We like open questions. All right.
There's a lot of open questions here, yeah.
I have another question.
Yeah.
So very nice presentation. Thank you. So Steve and picket fence, they tend to occur almost all the time, although we know that there is Steve without picket fence, and I think there is picket fence without Steve. But the mechanism that you are explaining basically is completely independent to what we try to use to explain Steve, because in Steve, if anything, you mentioned something about these strong flows that are westward, that implies electric fields that are perpendicular to the magnetic field. And you are talking here about electric fields that are parallel to the magnetic field. So it seems like the two theories are somehow decoupled or independent. Is there room to put them together, or this is something that's the way it is?
I think there's certainly room to put them together. The parallel electric field, so going back to the modeling done by Carlson for the enhanced aurora, which I alluded to, he has those parallel electric fields essentially arising as a consequence of how currents have to close in the lower part of the ionosphere. So when you have particles coming down, right, you need somewhere for those currents to go, because you can't just have currents disappear. And so there's likely something going on with similar in Steve and the picket fence, which is to say that you have this upper boundary condition of these fast flows with Steve, and there needs to be some sort of closure in the lower ionosphere, which might be where these parallel electric fields are arising from. That's something that we're actually working on right now, but don't have firm results on yet.
Okay.
Claire, on the at the bottom of those picket fence streaks, sometimes there's these things, I think they're just called streaks. They sort of spin off from to the side. Are they created, or do you suspect they're created similarly, or is there something different operating with those features?
So not entirely sure. I think you're alluding to Josh Semeter's paper, looking at those streaks. So it's possible, I think in that paper, they're talking about how those might be a consequence of turbulence at the bottom of the picket fence. And that might hold true as here as well. Essentially, it takes about a second, a little bit less, for the oxygen to emit that light once it's excited. And so if it's kind of breaking off and moving away in turbulent eddies during that time, that could be. So essentially it's excited where you have the parallel electric fields, but then it's moving away and emitting the light after. That's a possibility.
I see. Is that created through heating of the various atoms, through collision? Is that what creates sort of a drift, or is there some kind of a very high altitude atmospheric wind of some kind?
It could be a couple of things that are creating that. There are winds up in the thermosphere that do, push things around up there. But I'd say it's probably more likely to be some sort of plasma instability in the ionosphere or something else that's going on. But again, open questions. Just speculating at this point. Don't take my word for anything here.
No, thank you very much.
Yeah.
Hey, Claire, this is Jeremy. If I could ask, what kind of, in terms of collaboration with the Aurorasaurus community, I imagine collaboration means providing imagery or sort of just our experiences and seeing things, but is there any specific kinds of imagery, time lapses, or maybe types of imagery that we should try and go out to capture that would help answer some of the enhanced aurora questions? Some examples would be higher cadence imagery versus lower cadence, or video, or maybe having multiple cameras, say 10 or 20 kilometers apart, do triangulation. Is there anything that would really help answer some of these preliminary questions about enhanced aurora that are coming before the mission? Thanks.
Thanks for revealing the name of the mission on the recording. But yes, no, that's a good question. And that's something we can also talk a little more about offline. I think the goal here is to understand how often it occurs, how long it persists when it occurs. And essentially, the big thing is whether we would be able to hit it with a rocket, which is to say, is it stable enough and long lasting enough that once we see it, we can confidently say, finish our rocket countdown, and know that our rocket will be able to get there and hit it in the time it takes, to finish the countdown and for the rocket to fly, which is a couple of minutes. And so just having examples of, essentially just collecting more examples, looking at the conditions under which this occurs, the type of aurora under which this occurs. And then if we can get altitude information, do the triangulation, that would be fantastic. Right now, we're sort of assuming that it's around the same height as the picket fence, so around 100 or 110. But more precise information about that would be fantastic. And I would love to collaborate with folks about getting measurements of that, absolutely.
The really raw images without additional processing are definitely preferred because, you're talking about the color ratios as well, which is hard to get maybe from uncalibrated cameras, I guess, or like everybody's varies, and also varies if you can vary it deliberately in post-processing. And then secondly, there's a lot of post-processing that enhances boundaries and streaks and gradients and things like that. So I think for this kind of thing, that's another thing to reason to avoid that.
Absolutely, yeah, those are really good points.
And you probably want it stable for at least 10 minutes, usually, yeah, to raise the count and have the rocket actually reach the region. It takes a while.
That's right. Yeah, 10 minutes is about the benchmark that we're hoping for.
Got some cool photos in the chat.
What
Very cool
the-
photos.
Oh, sorry.
Go ahead, Bob.
Oh, I was just going to ask, what does a rocket launch cost? I've just been curious because it would seem like it would be a very expensive venture.
So funnily enough, right, when we're proposing the rocket, NASA has this program which is called low cost access to space. So NASA actually considers these are, rockets, balloon missions, that sort of thing. They consider them low cost, which means that they cost less than a few $1 million. I think NASA has a sounding rocket program, and they tend to provide the launch vehicles, so the actual rockets. They're many of them are actually leftovers from military rockets, and then they're repurposing them now for science. They have, a big warehouse full of these that they launch. But so they provide that. They provide a lot of the ground support and the team to, actually build the launch vehicle. And then on the science end, we're the ones responsible for obviously the science questions and then building the instruments. And, they work with us to help integrate those into the payload. So on our end, it's probably a project that takes about 3 years, and we get about $3 million to do it.
Okay, well, I thank you for taking the time to elaborate and answer that. I wasn't aware, especially of the big warehouse full of rockets.
Surplus.
Surplus.
And that's a fraction of the cost of a satellite mission. So most satellite missions. So the Sounding Rocket program also historically has been a really great place for training of experimentalists. So students and folks on, shorter missions. So that's really great.
Great.
Let's see. More questions? Some folks we haven't heard from, perhaps? I was going to say there definitely were some people that assumed that the picket fence was precipitation, but that was actually something we were pretty careful to say in the original Steve paper, that we couldn't say much about the precipitation. There was very little precipitation, but it was still a possibility. So, there's
true.
different.
No.
There's
your
always
paper
been
was
a
careful
variety.
about it.
Yes, yeah.
For
There's
sure.
always
There
been a
were at
variety of
least
views.
there were at least 1 or 2 papers that were explicitly calling it precipitation.
Yeah.
So, but I think now the community is pretty firmly moving into it's probably not precipitation camp.
Yeah. I also kind of, because I don't know, have a history with some of the more unusual kinds of aurora, like the black aurora and just other terms. I've always been more on the camp of this is just unusual aurora, like a more broader definition of aurora. But that is also like it's driven by the same system, right? It's obviously not driven by the precipitation, but to me, that's not the critical part of the definition, but there definitely are other. I'm probably not in the majority on that.
No, that's fair. I mean, there's an argument that you could call any optical, arcs in the sky, you could call that an aurora. But I think we just want to make sure to distinguish that, there's lots of different sources for where these are coming on, whether you're looking at, the SAR arcs or Steve and the Picket Fence or regular aurora or tall red streaks or black aurora, like you're saying, there's a whole zoo and there's lots of different ways to create the light as well.
All right, more fun stuff in the chat here. Reference to Wallops Flight Facility and their rockets. Jeremy, do you want to share a little bit more about the image that you found at all, or?
Okay. There was a sub discussion in the chat where somebody, I think Christian, mentioned fragmented aurora something, FAEs?
Emissions, yeah.
Emissions, my apologies. And they kind of looked like a single picket from Steve that didn't have the periodicity. And I was going through some images a couple weeks ago from an all-sky camera, and there's a instance of just an isolated green blob that had the same sort of contrast and greeniness of Steve or these FAE, or sorry, not Steve, of the picket fence or these FAEs or GBRs now, somebody's saying. And it's kind of like, what is that green blob is the game going on. So that was the image I shared. Was there an all-sky image? There was a KP8 and a long distance from any other auroral emissions. There were suddenly 2 green blobs that emerged for about 1 minute or so with that distinct kind of like a single picket look to them. So that's what's in the image.
Was that after a Steve, or sorry if I missed that?
Oh, no, there was no Steve associated with it from what I saw. This was right after or after or during a KP8 event, and it's definitely mid-latitude looking north. But anyways, yeah, I didn't want to draw any major attention to it or anything. I just was kind of curious if that was an FAE, like how we in general categorize phenomena and come up with like how do you separate all the different kinds of green blobs is sort of the thing that comes to mind.
Yeah, there's a
phenomenon categorizing them.
You've probably aware of there's a paper by Josh Dreyer et al. I think it's a 2021 paper. But that's, talking about those fragmented aurora-like emissions. And they don't have to be in the subauroral region. In fact, the ones that they're talking about are more in the auroral or even on the poleward boundary of the aurora, but they do look a lot like picket fences or just like blobs up there. And they're doing a lot of work on those up in, like I said, there's the group in Europe that's working on them. But preliminary analysis says that they are also too green. So we're sort of collecting examples in this zoo of too green aurora that might be created sort of right where you're seeing the light in situ.
And the FAE are like kind of very new, so they're not necessarily that well documented as far as like if you have a KP8 event. We have probably no idea if there's going to be this thing or some other blobs because there's other kinds of wave particle interactions going on that could cause some unusual subauroral emissions. Yeah. I think Joshua Dreyer, 2021 is the paper that Claire just mentioned, and maybe we can get that in the chat. And And we should probably sort of wrap up here. Thank you so much.